So I will basically touch three themes, and I don't think we should really fork, because I hope I will cover all of them. It will be area derivative without divergences, exact factorization of a loop equation, and some physical multi-instanton vacuum. Then there will be some topological stability, which will be quite unusual for the string theory. And then it will be some more details about building of actual minimal surface, very special minimal surface, which does solve loop equations and provide the confinement. It's not usual minimal surface. So in the end, we are going to build the continuum framework to solve planar QCD, which will be the subject of the next two lectures. But today we'll cover the first very important step, namely the firm background of Hodge-dual minimal surface, which is needed to solve the theory. So let's start with this momentum loop equation. In the lecture number 2, we found that momentum loop equation, though looks very nice, it doesn't have any singularities, no delta function. It is totally polynomial and differential, so it looks like it allows a power-like solution, but that solution surprisingly does not hold. It breaks. Equations, there are more equations than unknowns in this Taylor expansion of parametric invariant loops. So that means that the true solution is not what we thought. It's not something which is expandable in Taylor series. It's something more singular. There is a difference between infinite and singular. So Wilson loop has singularities in the sense that it has divergences. There are singularities at certain shapes of the loop. And momentum loop equation doesn't have any singularities. There are no delta function. Everything in that equation is finite. However, the true solution is not something which you expand in smooth power series. And by the way, to answer Nima's question, which he asked at last question, yes, there is a general proof that if there is an expansion in this Taylor series with these invariant tensor coefficients, then you could explicitly build the operator. It's called Kunst algebra and space of words. You take space of words. In the space of words, you explicitly build the operator representation for the coordinate x, and that coefficients of operator expansion involve these.
But you're saying, so everything which has a polynomial expansion in P can be written as an e to the I x mu.
Yeah, there is transformation which explicitly builds x mu in terms of cumulant coefficients which are related to these correlations. It's some very well-known relation between correlation functions and cumulants. Anyway, that doesn't help because in the 8th order there is contradiction, which means the whole expansion is wrong. And that's very interesting phenomena. And that tells us something about string theory, that you really should solve not the scalar equation, which everybody solved and called it loop diffusion or loop Laplace equation, but you should solve vector equation. You should not forget that Young-Mills theory is a theory of vector fields, and there are 4 equations, not 1. And that is the origin of these inconsistencies. They are inconsistent in higher orders. But there is exactly a solution which solves all 4 of them, and that's what I'm going to describe today. So the solution which we tried had the form of you have the left side of the equation, and you said, okay, the right side is O of P cubed. So if W is constant and L operator has order 3, then it will iterate. Next term in W will be P squared, and that will again balance. So you will start building term by term, but then it breaks. So something else is happening. Well, I can tell you what is happening, and it's, if you think about that equation, apparently there is a zero mode. That operator L nu is not invertible. There is a zero mode of that operator. And what does this zero mode mean? This zero mode mean in ordinary coordinate space the solution of the loop diffusion equation. And what is loop diffusion equation? It is translation of the classical Young-Mills equation into loop space. So there is some non-trivial vacuum with some non-trivial background field, apparently that's the only way out of this problem. So there should be some, it's called master field, it's fantasy, which exists for many years. You cannot really build such field in physical space because for example, instantons do solve Young-Mills equation, but they have shape and positions, so you have to have infinite combination of instantons with certain coefficients. It's integral over very complex moduli space, and then you maybe get some wave function which is translation invariant, but it's totally hopeless to actually build it. Nobody managed to do it. People try to do some instanton gas, but that's at the level of phenomenology. Here in the loop space, amazingly, it can be done explicitly. And that's first miracle I'm going to report today. So this problem of the vacuum is actually a problem of the vacuum, of course. What is the vacuum? Equations of motions don't tell you what is the vacuum. They tell you what happens, but you don't know what are the classical solutions on top of which there are these fluctuations. So you have to specify what is the vacuum state. So it turns out you can do it in loop space. Let me explain how. It's actually surprisingly, shockingly simple. Remember that area derivative is just antisymmetric part of the second derivative with respect to velocity of the loop. You take second derivative velocity of the loop, which is in general symmetric function of both angles and indices. But if symmetric function could be either symmetric in both or antisymmetric in both. So you pick the term which is antisymmetric. In other words, you take antisymmetric part of that index and then tend the angles to each other. And whatever survives, if it survives, is called area derivative. In case of the ordinary path exponential of the gauge field, you would easily see that what survives is the F mu, the field strength. For that, you don't need any singularities, just ordinary classical field like constant, it's called Schwinger gauge. Gauge field, which is F mu x nu, which is linearly dependent on x, but in non-abelian theory, that's non-trivial field. And for that field already, there is area derivative. These velocity correlators don't commute. I mean, they commute, of course, but there is antisymmetric part in the second derivative. Anyway, that's a kinematical identity. And that's the definition of the area derivative. Now, the operator on the left side of the loop equation is a third derivative. So this area derivative brings two derivatives with respect to velocity, and you add the third one, and again, you take the difference between angle to the left of these two involved in area derivative and to the right. And when you do this difference between left and right velocity derivative, you just insert the commutator. Remember, every velocity derivative brings in covariant derivative. So if you take the difference between left and right, you'll get commutator. So this thing is exactly the Young-Mills equations of motion. So you need to find such W which satisfies this equation of motion. And then you implicitly solved over all classical solutions if you find the one which is translation invariant. And indeed, if you find such solution, let's call it S of C, some zero mode, which satisfies, which is a zero mode of operator. Exponential of that zero mode is also zero mode for a very simple reason, because I explained that there is a Leibniz rule, so exponential any function of zero mode is also zero mode. If you take operator L of any function of S, it will be operator L applied to S times derivative of this function. So this exponential will also be the zero mode. So that will be solution of the classical equation. Now, ta-da! If there is area derivative is self-dual, then it will automatically solve the loop equation for the same reason why instantons solve the field equation, because there is a Bianchi identity which tells you that if f mu is self-dual, then you could say f mu is epsilon times f, and then you say, okay, then d mu f mu is epsilon times df, and that's Bianchi identity. So by virtue of Bianchi identity, any self-dual field, and that's a big observation of the instanton theory, has topological meaning, of course. Every self-dual field satisfies equations of motion. For us, that means a remarkable thing. We found a zero mode. Only if we find...
Can I ask a dumb question? Would the entire story with loop equations, everything, would it go through the same if we're doing self-dual Yang-Mills rather than full Yang-Mills?
What do you mean?
If we imagine doing the path integral for self-dual Yang-Mills rather than full Yang-Mills, does it make any difference?
Well,
how do you know this whole thing is not a solution to self-dual Yang-Mills at strong coupling?
Oh, because I will solve not just this, but also the term with the right side, which will not happen. Mm-hmm. Yeah, indeed, the zero modes could involve just integral over self-dual field.
Right.
But if you have not just zero mode, but something else, then it will be a different story.
I think maybe, well,
you're right. If I say that is the end of the story, my solution for loop equation is exponential minus s, yes, that is the solution, which is sum over self-dual field. See?
Right.
But I'm not going to stop there.
But you're
that's one of the factors.
That's one of the. But you're saying that the whole answer looks like the product of what you would have gotten if it was only self-dual times something perturbative.
That's right. And the reason is that you see, loop equations are equations of motion.
Right.
There must be ambiguity of choosing the physical vacuum, and that ambiguity is exactly this dressing factor, because you should be able to choose different vacua.
But if you did not have the perturbative part, let's say you didn't know about the perturbative part. If I just said this is the full answer, you would know this is not yet correct. How would you know this is
it will be the full answer of the thing which is called Yang-Mills gradient flow. There is this beautiful mathematical problem. Time derivative of A equals divergence of A. That's a
that has a fixed point, which is self-dual.
Yes.
I see.
It's the vacuum theory.
And they didn't know that. They knew that they knew, of course, that Yang-Mills gradient flow has a fixed point, which is any classical solution, including instanton or multi-instanton. But they didn't know that there is explicit formula in loop space for the surface which satisfies that. That's a new thing.
But if I wanted to, but this question that we keep circling around, which is I mean, there are some things that solve the loop equations for big loops, right? Large loops. It's going to be relevant for confinement and so on. The kind of big physical question is whether there is a consistent solution that interpolates from that to what we know the perturbative.
That will be subject of next lecture.
Okay.
Today I'm going to talk about this confining factor, which basically dominates a large loop.
That's fine, but we agree that if we just had this self-dual factor, it would be the answer in the self-dual Yang-Mills theory, and that would not, obviously not interpolate to anything that has physical gluon.
And I wouldn't dare selling you that half-cooked theory.
Yes. It's slightly, I mean, it's slightly funny that the exact answer is just a flat-out product between perturbative and self.
It's not perturbative. It's ambiguous definition.
Okay.
Because what is sum of planar graphs if there is a factorial number of them, or they are divergent themselves because of a normal one? So I guess it's ambiguous.
But maybe we'll come to this. But what I don't have a feeling for yet is, I mean, when we're just solving classical equations, we can look for self-dual solutions. That makes solving classical equations easier. The fact that makes it easy to identify solutions does not mean that that's what all the solutions that we care about look like. I mean, almost the opposite. The most of the solutions that we care about don't look anything
I'm
like.
not saying that I found all possible solutions of mechanical Migdal.
Yes. You found a
But
solution.
if I found one confining solution which
Yeah.
makes the experiment, I would be happy already.
Okay, all right. But although okay.
Look,
No,
until
sure,
recently there were none for 50 years. Now you're saying, oh, why only one? That's unfair.
No, I'm not saying why only one. I say why this one is what I'm saying. But anyway, yes, I got it.
So, Lima said he had a dumb question. That wasn't a dumb question. I'm gonna ask the dumb question.
Good for you. That's
By the way, I forgot to say, I want to make an announcement. I'm going to, yes, about the questions.
Yes.
Next time, I didn't bring it this time, didn't dare, without your approval.
This is my question. I thought I was gonna win.
Oh, I'm going to bring a very good bottle of wine of my cellar, which I ordered from the high-rise Argentina's vineyards, my favorite Malbec. I'm going to bring it here and deliver whoever will ask the toughest question. Well, we're going to vote. We're going to vote. No. You want me to decide? Yeah, because it's about me feeling most.
Take myself out of it because but how about this? I will act as judge.
Yes, okay.
You and I will act as judge.
And for that, of course, you deserve the first.
I certainly do.
First glass. Okay, anyway. Yes.
Why is there no I in the function block?
Why is what?
Why there is no I?
Because in Euclidean space, I'm talking about Euclidean space, and when I will come to Minkowski, I will not forget my I.
I see. For a second, I thought we were.
No. Yes. So epsilon is just plus or minus 1, and duality means Euclidean duality, and that's enough. So if dual of this S is either plus or minus itself, then you say, okay, area derivative is plus or minus its dual, and then you say, aha, then divergence of dual is identically 0 because of Bianchi, therefore self-dual, any surface with self-dual area derivative satisfies the loop equations, which means it represents some classical field. Moreover, it represents some infinite sum over some instantons hidden behind the hood. Of course, I cannot tell which one, how they are actually built, but we know that they are there, otherwise it wouldn't be self-dual. So technically, this identity is identity for third dot derivative, third derivative with respect to velocity, and that's proven exactly the same way as the Bianchi or Jacobi identity for the triple commutator. And we know already that derivative from the first identity in the first lecture, we know that the derivative with respect to loop velocity brings down covariant derivative. So if you take antisymmetric combination, it will be triple commutator, and triple commutator satisfies this identity. And therefore, the self-dual, any functional with self-dual area derivative will satisfy the loop equations. And therefore, because of Leibniz property, you may say that W is exponential minus this some coefficient times this S, and it multiplies by something which is really not uniquely defined, because this W fluct could have non-perturbative part, which will renormalize kappa, of course. But what we really know about the perturbative part or fluctuative part is it doesn't have that. We were looking for some source of this thing. The beauty and remarkable luck of this self-dual area is that its area grows exactly as ordinary area. Moreover, it's exactly proportional to ordinary area. The surface is different than minimal surface in 4 dimensions, but at the extremum, the minimal area is up to renormalization of this coefficient kappa the same as ordinary minimal area. And that means immediately we see the confinement mechanism. I would expect you to say, confinement. You just have proven, I didn't prove confinement, of course, but I presented very explicit mechanism.
Kappa is not zero. How do you know kappa is not zero?
Wait till the end of this lecture. I relate it to the gluon condensate, which also could be zero.
That's right. Yes. How do we know the gluon condensate is not?
But not in this world.
But you don't think, so you're making a distinction between a non-zero gluon condensate and confinement?
I'm saying this factor definitely leads to confinement, and then when I consider it at smaller scales, I relate it to the gluon condensate. They are different sides, of course, but you could relate them. You could find such a, well, I don't want to go ahead.
Sorry,
Yeah.
what I want to ask is, are you assuming there's a non-zero gluon condensate? Is that part of your, do you have to assume there's a non-zero gluon condensate to find that the kappa is not zero?
Well, I will relate kappa
Yes.
to the term in the operator product expansion, which is gluon condensate.
But
So they are related. If one is non-zero, then another is non-zero. Also, I relate the quasi-classical trajectories to this kappa and see that it is exactly proportional to what is called string tension.
okay. Just very naively, it's a very naive comment, that of course in perturbation theory, the gluon condensate is zero. And if there's no confinement, you'd expect the gluon condensate is zero. So saying there's a gluon condensate is not that far from saying that there's confinement.
No, it is very far.
You think it's far?
One is a small of the microscopic property of gluon vacuum. Another is stretch of that same gluon vacuum over some invisible membrane between quarks.
But it's a translationally invariant object. It's a gluon condensate at zero moment.
You're telling me that confinement is obvious. I agree with you.
No, I'm not saying it's obvious. I'm just saying, but I'm saying that confinement most naively is that we don't see objects with color, and that means that things like the gluon condensate should have vanishing. I mean, certainly in perturbation.
Gluon condensate has nothing to do with invisibility of the color object. No.
Yes. No,
Gluon condensate.
fine.
Yeah. No. What is non-trivial is the strength linear force. I mean.
Yes, of course. I know.
Yeah. And that is a mechanism of the linear force. One thing is finding mechanism, another is proving mathematically that it works. That's a different level of problems. Anyway, I wanted to explain to you that what this dressing factor, being self-dual, must be a combination of self-dual fields with some unknown weights, right? What else could it be? If it is gauge invariant and self-dual, satisfies the self-duality, and specific duality, there could be a self-dual and anti-self-dual, and that means, say, self-dual, kappa chi equal 1 means sum of positive, and chi equals -1 is sum of unintervals. Anyway, it doesn't help because I cannot tell you what are these Wi, and I don't need to because in my space, in loop space, I just have to find this S. And that's infinitely simpler than this, because I'm going to present to you exact answer right now.
Sorry, maybe you're just saying this, but how do you know it's self-dual and not anti-self-dual?
Chi, there is a sign. Dual F equals either plus F or minus
But
F.
which one are you choosing?
Later. Remarkably, they have the same area, so I don't need to specify. Technically, I could just add them with equal weight, exponential sum of them, but
Okay.
the result will be that if you are only computing the W, then they have equal, well, that's a little paradox I'll explain later. They have equal area, but not equal area derivatives. Anyway, if you look at this equation and you say, aha, I have this dressing factor, which passes through the left side. If I substitute this to the left side, this factor just passes through because L annihilates it. It passes through, and then I'll get L times W. So if L if W fluct satisfies that same equation, then this is just invariance of the equation. You could multiply it by this factor e exponential. Now, when can you multiply? Not always. You can multiply when your area is additive at self-intersections. Because on the right, you'll have two W's. Each one will give such a factor, and they must be additive. On the left, you'll have W for the whole loop, which is H-shaped. On the right, you will have product of two W's for the petals. So if this S is additive across intersections, then indeed it will cancel on that equation. So you see, it's much more than just a requirement of self-duality. It must be some solution of minimal surface which has additivity at self-intersections. And this solution is known for many decades. It's called Goldschmidt solution. And we're going to discuss it a little bit later.
Sasha, when did we transition back to position space? I mean,
because we could not formulate it in a simple way in momentum space, because we found that in momentum space it is
right.
non-analytic, therefore we cannot expand it. So yes. I will find it in loop space where it is simplest, and then I explain what it means in momentum.
Okay, but then, so was momentum space then an irrelevant detour?
It proved to us that W of P is finite, which is non-trivial. There are no divergences. It was needed to understand, it was not a detour, it was natural step, and it is important to understand that it doesn't work, because of that we understood that we have to solve vector equations.
Okay.
It is just something which helps us understand the meaning of the loop equation. Yes. Solution, from the point of view solution, I wouldn't need to go. Yes. What do you ask?
I guess you had a slide where you said that the zero mode of the momentum space Wilson implies the zero mode of the position space. Wilson.
It's not quite the same. No. Well, yeah. Well, I will say, I will in a couple of slides, I'll discuss exact relation between the zero mode in position space and momentum space. So let me answer your question later.
But just to say again, you're dividing the W fluctuate in the other piece. Is it just a general fact that if I take any solution W of C of the MM equation and I multiply it by this e to the minus kappa S, I get another solution of the MM equation?
Yes, that's invariance.
That's okay.
That's invariance. That's invariance of equation which was hiding in plain sight for 50 years. That's surprising invariance of that equation, and that invariance reflects ambiguity of choice of the physical vacuum, because that S corresponds to what is the structure of, there should be some ambiguity, because this loop equation is just equation of motion.
Right, but then so somehow because of this ambiguity, any solution that you write down, I'm going to say there's another solution, which is your solution times, for example, I can take your solution and multiply by e to the plus kappa S and get
You are right until I tell what is W fluct, which is really solving everything. Until I specify the whole combination, it's really just ambiguity, invariant.
There's some ambiguity and somehow matching to the correct perturbative short distance physics.
It's not a unique, yes. Yeah. Well, the only thing you can say, if the loop is large, what is called fluctuative or perturbative doesn't make it, because that's otherwise we would call it confinement, right? Because we know that in perturbation theory there are perimeter terms, but there are no areas.
Right.
So let me just explain what it is, and then you will understand that there is an area term. So additivity is a very important part, because we're looking for very specific minimal surface, which is additive at self-intersections. Only then it will pass through the loop equation. So let's consider this thing, right? So here is the self-intersecting loop. On the left, we had the whole loop, which is W for the whole H-shaped loop. And on the right, we have product of two loops for this one and for that one. So in exponential, on the right, you'll have exponential of sum of the minimal surfaces for these two disks, and on the left you will have, on the left side you will have exponential of the minimal surface for the combination. But as we know from the theory of minimal surfaces, and everybody could see it in experiments, that if you, for example, start folding these two loops on each other, so they become closed, then there will be a handle. And minimal solution at some point will not be independent windows, independent minimal disk surfaces covering each disk, but it will be just one cylindrical surface covering, connecting them. So plateau, the physical surface, the soap film surface, which was assumed to be true for the QCD for 50 years, will have this problem. But so it will not solve loop equation. But for example, here is what happens if we take actually the soap film and make these loops close enough. They will make a catenoid, and that, of course, is not the same as two independent disks. If you move them farther, then catenoid will break in the middle, and you'll get two trivial disks covering each loop. So there is this phase transition, which obviously shouldn't be happening in physical world. At least, I mean, it happened in physical world of soap films, but it shouldn't be happening in QCD. So in QCD, it is forbidden. So let me tell you something interesting. So we're not solving the plateau problem, which is a minimal surface. We're solving QCD equations of motion. So what we need is this so-called Goldsmith branch, these joint disks, rather than complex topology. And by the way, I would expect your questions that, oh, wait a bit, what about real cylindrical strings? They will enter in the next order of one of our experiments. We are talking about the leading order, and in that leading order should be no handles. It is just one minimal surface for each loop. So is this a Goldsmith solution stable? Yes. There were theorems, it was studied. It is local minimum, so it is stable. But globally, no. There is topological barrier making it stable against small fluctuations, but if you make a big fluctuation, if indeed you have a physical degrees of freedom on the surface, they will, with some probability, make a jump, and then they will have a break. But that's not what we are describing here. We're just solving loop equations. We are not quantizing string. It's a different philosophy. We don't take string as a theory of everything and apply it to everything. We are trying to solve existing gauge theory. And whatever is good for that gauge theory is good enough for us. And there's so-called White's bridge principle, meaning that when you take this loop and start moving it so it starts getting close to intersection, then this bridge between these two parts becomes thinner and thinner and eventually becomes infinitesimally small, so you'll get this separation. It's not a jump, no phase transition, it's continuous transition, which is good for us, because that's what we would expect. So what's the physical origin? Well, we have exact equations of motion. There is inherent ambiguity relating to a physical vacuum. We should choose the solution with the minimum vacuum of QCD, not minimum vacuum of the surface energy of the rubber band. If there is a difference between the two, then we should forget about the rubber band. That was a phenomenological model. We should always choose solution of the quantum theory, because that is what we're actually minimizing, the vacuum of QCD, not vacuum of rubber band. So also it's a mixed state of multi-instantons, like I already described. And the miracle is that the surface, which we're going to build in a moment, actually sums over all instantons. I don't know how, I cannot describe how, but it sums, apparently. Okay, now let's construct this. Now I'm going to tell you something really new. How to build this self-dual minimal surface. It's rather simple, actually. You embed this physical loop in 12-dimensional space. So you take coordinate x mu and add one more index. And that index will be analogous to gauge index of SU2. It runs from 1 to 3. So you have this R3 times R4 space. And in this space, you consider the area of some surface with the following natural area element. It's just Hodge product of the gradients of x, and it's summed over all internal components. Let's call it internal symmetry, this index running from 1 to 3. So there is this symmetric degenerate, I would say, area derivative. But on the bound, and we minimize this area under condition that this area element is self-dual or anti-self-dual. So chi is plus minus 1. So minimize that area, imposing extra condition. And on the boundary, I relate this field to the loop. And because loop has only 4 components and my gauge field has 3 more, I use these Hopf indices, which exactly map the 4-dimensional space into the Lie algebra of the SU2. So basically, my x mu is element of the SU2 Lie algebra. And from the point of view of O4 rotation, xi mu rotates as one of the 2 subgroups.
I got lost. I'm sorry, Sasha. Can we start?
Sure.
Again? So what is
Imagine the surface in 12-dimensional space, and coordinates of that surface have vector index mu and azeotropic index I.
What is I labeling? What is I? Where did I come
It's some internal degree of freedom.
Where did 3 come from?
3 comes from generators of SU2.
Where did SU2 come from?
Of 4. O4 group is equivalent to 2 SU2s.
Okay.
Left and right.
Okay.
And self-duality actually means that your area.
So these x's are Euclidean space-time spinors.
You may see them as that. You may instead of I, you could use matrix. You could say it is rather 2 by 2.
Yeah, sure.
Matrix.
Yeah, that's right. Yeah, that's right.
They are matrices.
That's what I meant. I meant
Yeah. They are you may see them as matrix field. It's matrix field like gauge field of SU2. Basically, you may think that they are like gauge fields of SU2.
Yes. Yeah, I understand. I just wanted to know where the SU2 came from. The SU2 is the SU2 cross SU2 of 04.
Yeah, right. It's nothing to do, but instantons, as you know, map.
No, I know. It's
one into another.
Right.
So from my point of view, it is just using one of the 2 SU2s in 4-dimensional rotation group and saying that if I want to have self-dual surface, I have to use one of these 2 subgroups.
And now, so in the space of x mu I have a disk, a 2-dimensional disk in this funny space.
No. You have disk in a complex plane. I mean,
normal.
Yes, yeah. You just map it.
Right.
Yes, the boundary of this disk is.
I see. Sorry, I didn't. Okay.
So here is the mapping.
I have normal
loop C, and you map it into X using these eta indices, meaning that rotation of C translates into the left SU2 rotation of Xi, or right SU2 rotation. And that's important because that is a mechanism how you could make it self-dual. So the self-dual solution is simply this.
But sorry, I mean, you're going to tell us, but I thought a little while ago you were telling us that when all the dust settled, the exponential just turned into the normal minimal area. No?
It's a value of the area is the same as minimal area.
Right, but
when you find the area
understand.
derivative,
Yeah.
you should go beyond the value because you should think of the whole region, 12-dimensional space.
This functional is not the same as the area in general, but its value, but its extremal value is the same as the.
That's right. And its first derivative is 0, but second derivative depends on its embedding. So the thing is that when you change,
And the second derivative matters for the equation.
Yes.
Yes.
Because area derivative is antisymmetric part of second derivative. So what happens is the following. This boundary values, this Dirichlet boundary value, tells you that when you change the loop C, the whole 12-dimensional field changes. It's rigidly tied at the boundary. And therefore, you cannot neglect this 12-dimensional space. And therefore, and that is how you get this self-dual area derivative. You see, the 12-dimensional field X is rigidly related at the boundary to the loop. So when you find area derivative, you effectively change the whole surface, not just its boundary. Anyway, the solution is very simple to what people find for the ordinary minimal surface. So ordinary minimal surface is the same thing, but without this eta factor. So ordinary minimal surface, okay, my X is just sum of self-dual and anti-self-dual, and that's by definition of the minimal surface, because then, the functional reduces to the Dirichlet functional, and the harmonic function, which is this, will solve it. So basically, I'm looking for harmonic function, but combination of harmonic functions. Now, when I do that, I easily find two things. So the boundary conditions for this function f will simply be the same as if I was solving ordinary minimal surface, right? Because these eta factors were just the same as here. So the boundary values of this f are related to the loop. So finding this f is exactly the same problem as minimizing the ordinary area in physical four-dimensional space. It's just a different embedding. I'm using ordinary minimal surface, and I embed it in 12-dimensional space instead of four-dimensional space. And but what happens with this area element is interesting. It's not just this f mu times f prime mu. It's combination. It will have this f mu term plus chirality times dual. So what will happen is this is explicitly self-dual form, right? If you take some antisymmetric tensor and add plus or minus times its dual, by definition, it's the same as dual or anti-self-dual projection. So this solution actually explicitly solves the condition of self-duality. So that is a kinematical solution of this self-duality. And dynamical part is solving the minimization of the area with this boundary condition. So this exactly, this ansatz exactly satisfies self-duality, which I didn't understand in the very beginning, but now I understand it very clearly. It's a very simple thing. And so area derivative is dual, but if you compute the area, what will happen is that you could choose the, in the metric, you could choose the Virasoro constraint. You could choose such a metric that second derivative, ZZ component, the metric is conformally equivalent to diagonal. The metric has, in general, in these coordinates z and z bar, it has z component, z bar component, and the mixed component z bar. So these off-diagonal zz and z bar are 0, and then you are only left with the mixed component. So that means that this vector f prime is a light-like vector. That's called Virasoro constraint. And that's how the minimal surfaces are built in four-dimensional space. So this effective action, which is square root of this sigma squared, there will be this term, and then there will be this term will vanish, and you will get just this square root of square of this, which is just absolute value of mu squared. And that's what's called Dirichlet functional. That's something studied for many, many years. And it's not completely solved because this nonlinear equation is not completely solved. But it is solved in terms of twistors, and that will be the subject of the next lecture. Yes?
So this looks like it was basically independent of your 12-dimensional embedding space.
No, it is dependent.
So what I mean is the boundary constraints sort of.
I solved them.
Yes.
So this and that solves them.
So it solves the Hodge duality condition, right?
It solves the.
So then sort of.
No. The boundary conditions become this simple equation, this one.
Yes. So those are boundary conditions. Those don't depend on the 12-dimensional space.
Yeah. Yes.
Right.
So now I can forget about 12-dimensional space because my function f mu is 4-dimensional. Yeah. It is mapped in. So I have 4-dimensional complex curve. It's called complex curve. Yeah. F of z. F mu.
So currently you're working just in the 4 dimensions with the f.
Yes.
And then that will be sort of embedded into the larger space via the tooth matrices.
That's right. Yes. So this, basically internal geometry, I have the same as an ordinary minimal surface. But I have different embedding because I'm embedding it in 12-dimensional space. And that embedding matters when you compute the area derivatives.
So my question was, is everything on this slide basically in the 4-dimensional space?
Yes.
So it's not really, this is sort of pre the embedding.
Well, yes, this 12-dimensional space is a tool to prove the loop equations. Without this going to 12 dimensions, I wouldn't have this self-dual area derivative, so my loop equations will not be satisfied. And the point is that loop equations are dependent on external geometry of the surface, not internal. So where you embed your loop is important. If your loop is a boundary of, say, ADS, or it's a boundary of this 12-dimensional space, it makes a difference. In the same way, by the way, when you consider this ADS, you really, it mattered that your loop was boundary of this anti-de Sitter space. And here it's a different space, which is flat, no gravity, no anything. But in this flat space, I found the way to map the loop into that space so that self-duality is exactly performed. Now, there is this formula, which is also known for ages, how you reconstruct the holomorphic function from its real part. You add what is called Hilbert transform. Yes?
Can I ask another question? So
yes.
I'm still confused because it seems like you're solving the Hodge duality constraint condition just in 4 dimensions. But I thought that the toothed matrices depended on chi.
Yes.
So how is it? Yeah. Can you explain that? So if your Hodge duality condition is already solved.
Hodge duality condition in 4-dimensional space. Yeah. If you try to derive it from Lagrange Euler equation for the full 12-dimensional thing, you'll find out that indeed in full 12-dimensional space, the variation of the area, which is this functional, that variation of area in general becomes self-dual if you have this ansatz. So
I see. So in other words, you can solve the Hodge duality in 4 dimensions, but in order to maintain that sort of Hodge constraint into 12-dimensional space, you need to use these.
No. Condition that area derivative of the surface is Hodge-dual in 4 dimensions, requires bigger statement that it is Hodge-dual in this 12-dimensional surface, because this area derivative probes the edge of this 12-dimensional surface. So if there is this Hodge-duality in that 12-dimensional space, sigma mu nu sils is antisymmetric tensor with 4 indices, right? So if there is Hodge-duality in this 20-dimensional surface, then indeed its edge, which is loop, will be Hodge-dual in a sense of variation of the loop.
Thanks.
Just to be clear, everything ultimately is defined in 4 dimensions. The loop lives in 4 dimensions. There's some formula that only depends on the 4-dimensional data of C.
Yeah, but it's
you're-
complex
yeah.
and yeah, okay, whatever. Go ahead.
Right. I mean, I think this is the question. So, for example, you gave the ADS example. Well, in ADS, the W of C is purely a function of C.
And
Sure.
so it is here.
And knows nothing about how
And
you
so it is
extend
here.
it to
And
ADS.
so
and
it
so
is here.
But the extension into 12 dimensions is useful for what purpose? I mean,
To prove self-duality, to
is it-
compute,
yeah.
to prove, to compute area derivative of this thing, you have to go to 12 dimensions, because when you vary the loop in 4 dimensions,
Yes.
because of this rigid boundary condition, it varies the whole surface in 12
Let's
dimensions.
say you've never heard of 12 dimensions. In the end, you have a formula for W of C that only depends on the curve C
Okay.
drawn in 4 dimensions.
Let me,
Where does the 12 dimensions come in?
you would not be able to compute a second derivative of the minimal value if you only know minimal value. If I tell you only minimal value of the surface, it is not enough. I have to tell you the whole functional, and that whole functional is actually defined through 12-dimensional space. Only its minimal value is described by this holomorphic ansatz or by this thing. So what I'm saying is there is whole problem of finding minimum of this square root of sigma squared in 12 dimensions, which is in general non-trivial functional with boundary in 4 dimensions. Now, if I find the variation of that functional,
I mean, it's because you're trying to interpret it as some minimal area in 12 dimensions, right? But the actual
it's not interpreting, it's computing it.
great, but it's a super dumb question. I think we're both asking. If you give me the value of W of C for every conceivable curve in 4
Okay,
dimensions,
for that I have
why
a very
is that
special
not enough
example.
to,
For that I
that's
have
not
just,
compute the-
for that I have a special example, okay?
Yeah, I think this is the.
Here is an example.
Right.
Here is a function of 2 variables and 1 parameter A.
Yes.
Now, if you minimize it over y, you will get minimum at y equals ax, and this minimal value is x squared. Now, if you compute second derivative with respect to x before minimization, and then set y equal ax, you will get 1 plus a squared.
I fully understand, but there's kind of a.
So second derivative cannot be computed on the target functional. If you know minimal value of their function,
Sorry, if you're defining the I think if you're trying to define what the function is, the minimum of something, but forget that. I mean,
it is the minimum of something.
I know, but I think there's a super basic. I mean, the question is the 12 dimensions a tool or is it a necessary part of the theory? In other words, if I give you W of C for every conceivable loop C, isn't that enough information
I
to compute the
give you in this
by-
example
by-
f of
by-
x.
by calculus?
No.
Yes.
The minimal value of this function
No,
for
I'm not
every
talking about
conceivable value of x equals x squared.
No, but I'm not talking about the minimum value. I mean, in the end.
It
there's
is
a
I
W of
only
C.
can tell you
Yeah.
minimal value. I cannot tell you what is W of C. I mean,
I thought
W of
if
C is
there's a W of
defined
C
by
for every
as
C,
minimal
right?
value.
Well, if you want to define as minimum value, I agree. But in the end, there is a W of C for every curve C, right? There are some W of C.
Then I
curves.
say
Right.
W of C for every curve C
Yes.
is defined as minimum of this 12-dimensional
That's
function.
fine. That I'm entirely fine. But we just want to clarify that
So yes,
that
W of C as a functional of C,
yes.
not value, but a functional
As
of C,
a C, that's right.
is
As a-
defined as
yes.
a minimal value of this complex 12-dimensional functional.
And that
Then I
takes the
can
minimal value.
find the variations, and then I could take
But if someone just like handed you the values of W of C for 10 of the 100 curves that are all close to each other, just the numerical values of W of C for all those curves, then you could clearly compute the second area derivative. No? So we don't need
no,
no?
in the same thing, because there is hidden variable, which you already set to 0 when you found this minimal value.
But I'm not okay.
It just must
Yeah.
be wrong.
Yeah.
Well, in this
precise
example,
Yeah.
It's
Nima, in this example, you will tell me,
Yes.
I say that f is a minimal value over y
Yes.
of functional of two variables,
Yes.
right? So minimal value is always x squared.
Right. But sorry.
But second derivative of that same function taken at that same minimal value is 1 plus a squared, not 1. If you
okay.
know minimal value, you cannot yet compute the Hessian.
Yeah, no, this I understand. So in other words, if you define, let's call it whatever you're calling it, g of x, exactly, g of x is the minimum over y of f of f(x). Beautiful. That is x squared. I would say, well, okay, that's it. Now it's a well-defined question. What is the double derivative with respect to x squared is equal to 2? It's independent of a. Very good. Why is that the wrong answer? I mean, what I just don't understand is that the entire problem lives in 4 dimensions. If you told me that the 12 dimensions is a tool for computing something, I'm happy with that. If you tell me that the 12 dimensions is necessary for defining the loop equation,
Yes,
then
it is necessary for defining the loop
that's
equation.
that seems that's what seems very, very peculiar, right? Because
I cannot compute area derivative without going to 12 dimensions, because my boundary conditions, variation of my boundary conditions forces me out of my minimal solution. I go in transverse direction when I find the variation of loop.
but okay. I think, well, let's go on. I think we're going around in circles on this point.
Okay, well, anyway, the point is that I have the definition, which is the minimum in 12-dimensional space. That definition provides both the minimal value and the value of area derivative. Now,
No, but this is already a little bit funny because I would think that the MM equations to begin with live in 4 dimensions, right? I mean, are you saying that I cannot write the equations in 4 dimensions? Period. We're
no,
not talking about
equations
solving.
are written in 4 dimensions.
Okay.
But when I am varying certain 4-dimensional functionals, if I define these functionals as boundary values of some 12-dimensional function.
I know, but let's say but I'm just saying something. So, but it's really like this, like your example, right? In the end, the double derivative is acting on W of C, right? So if you give me W of C, then however.
Then I'm not giving you W of C.
Then
I'm saying stick to this 12-dimensional space because that's the only way to compute area derivative.
So
this I find, so you're really saying that the loop equations themselves cannot be formulated in 4 dimensions.
They are formulated in 4 dimensions, but
here's maybe one way of thinking about it. So in this sort of simple paradox, there is another thing that you could do, which is when you're taking the second derivative, but you still have y there, you could consider y to be a function of x. So it has to be included in the derivative. So it's kind of like, you know, this sort of, you're minimizing over it, but actually you should sort of consider it a function.
That's fine, but
that sort of feels more like a calculational tool then, if you sort of reframe it that way.
I mean, I'm just saying in the end that I'm totally happy to say that that W of C is computed by extending C into 12 dimensions or anything you want. I'm perfectly happy with that. What I'm not happy with is that I do not know how to act with a double derivative other than in 12 dimensions. That does not make sense to me. The problem lives in 4 dimensions.
let's
So we-
let's
we-
say, okay,
right.
I am giving you something which is singular, and the way I suggest, consider infinitesimal, very large string tension for that, right?
Mhm.
And find the sum over all surfaces, and those surfaces goes in 12 dimensions. Then you make a very, very large string tension, it will go to minimal surface. And in that limit, there will be no paradoxes. Because then, if you will compute the area derivative, it will still be in 12 dimensions, and then you will take the limit. So that's this.
So I mean, I guess maybe I would have been, maybe it would be a little bit, I mean, it'd still be a little bit strange, but still okay. If you said from the very beginning, everything is 12 dimensional, and there's some limit where it effectively looks 4 dimensional.
Yeah,
That would
when
also
I
be fine.
impose the minimum area, yeah.
But and maybe I guess we'd also be happier if we could identify that there's some singularity associated with the double derivative, purely in 4 dimensions that's getting somehow
Like anomaly, right?
something, yeah, something which it's just what the only again just say for the third time, it's not that having some space in which you extend something to define what you mean by functional of a loop is no problem at all, no problem at all. What seems problematic is to say that I don't know how to define what I mean by derivative.
No.
other than in 12
The key is the boundary condition. The boundary condition when you change the loop, which is bounding that 4-dimensional space, that boundary conditions means that that change of the boundary loop.
You're not talking about you're talking about the boundary conditions we imposed in
12 dimensions.
I mean, there are 2 things we could be talking about. One of them is boundary conditions we need to impose on the loop to define a minimal surface.
It's not to define the minimal surface,
It's
it's
to define
just
the
to
operator.
define the surface.
To define the surface, period.
Yeah, well, you have to have
Boundary
boundary condition. To minimize functional, you have to have
No,
boundary.
but you talk about minimizing. Well, I don't care about minimizing. I care about defining a double derivative.
But suppose you are not minimizing, they're summing over all 12-dimensional surfaces bounded in that sense by the loop. So at the boundary, that x is related to the loop by this formula. So yes, I'm summing over all surfaces, and then
Okay, anyway, let's.
okay, I think we should go forward.
Yes.
Yes, that's the point where I'm not completely happy myself. I just found the recipe which produces what feels like right result, what mathematically is correct, because I do have self-dual definition, and that involves this strange limit, but it works. Anyway, so in QCD, analog of that is this boundary. You see, at the boundary, this soft matrices are like this parameter A. That's what relates the functional to the boundary condition, and that's the elasticity.
Just ask one more time. So let's say someone, we skipped all of your lectures so far, and someone said, look, here's a great e to the minus s of c solves the loop equations. And you would say, in 4 dimensions, just no fancy stuff. E to the minus s of c solves the loop equations. And you're saying now, yes, it does solve the loop equations, but only if you think about the double derivative in 12 dimensions. Is that what you're saying?
I'm saying that if you naively take the minimal value and differentiate that, you'll get different result.
You'll get
different result. You will not get a self-dual derivative.
Okay.
You'll get result which I think is wrong, because there is a definition, 12-dimensional space, which gives you correct result, which is self-dual.
Can I ask, when we're going to come in the next lecture to your computation of the spectrum, blah, 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 does the 12 dimensions matter anything?
No.
There? Okay, so everything comes from e to the minus s of c in the naive way.
Yes.
So you can forgive me for being skeptical.
So you may say, no, I can tell you the following.
Yeah.
Sasha found the magic hand-waving trick to prove that minimal area satisfies the loop equation.
Okay.
By, in his imagination, projecting it in 12-dimensional space.
Okay.
I found the way to take ordinary minimal surface, embed it in my imagination in 12-dimensional space, apply array derivatives there, and get the result which satisfies the loop equation.
So it ends up being the normal area
Yes, it's a normal minimal area.
that everyone does.
It's a
Well,
normal
for
minimal
example.
area.
Not everyone does because it is Goldschmidt solution, the one which is additive at intersections. Not everyone does it.
I mean, so it's the one that.
It's not global minimum of the.
If I'm just writing down the action, I can write.
Yes,
it
yes.
as normal.
Yes.
And yet I'm supposed to see some chirality,
Yes.
because I'm supposed to get either a self-dual or an anti-self.
No, it doesn't matter. Because they're the same.
Well, areas are the
They're
same,
the same.
but area derivatives are not, of course.
But
So I take the
but
normal
Okay,
function-
let me find conciliatory node.
let's keep on going. I think the thing is that but it and I think you showed us before, or if not, maybe we could go through it. Without any of this formalism, I just give you e to the minus area, and it's kind of and one can see that there was a problem with that solving the loop equation.
If you substitute
Yes.
it in loop equation and literally compute area
Yes, yes.
derivatives, well, that's what I did in my
Yes.
previous work. You compute, and you
And
have.
what and where is the problem? Is it a singular? Is it
Yes,
some
it
singular-
is not zero. D mu f mu, no, d mu, I mean, it is not zero.
But is it not zero like in? some
It is in a
singular
very
case?
bad
But-
way. It is infinity. It is indefinite thing. It's epsilon divided by delta squared. There is a two.
Oh, I see. Interesting. I see. So that's what I wanted to see. What I wanted to see is that it's actually ambiguous.
Ambiguous.
It is ambiguous. Okay, all right. Okay.
It is ambiguous because there are two limits involved.
Okay.
One
One
when you
limit is-
apply
yeah.
along the loop, and another when you apply along the
I
surface.
understand.
So
Okay.
the ratio of two
Okay.
two small numbers enters in the result, and you don't know what you're doing.
Okay.
So
good.
the way to resolve this ambiguity is to say that you have to specify the embedding of your minimal surface.
No, if it is an epsilon over delta squared, why can't you just say send epsilon to zero faster than delta?
Because I'm not self-serving. I have to understand why I should do that. I mean, if there is no, it should be unique answer. It should not depend on any limits. It should be exactly zero. That's what I need. Well, it is exactly zero if you define it this way. If you define it through the 12-dimensional surface, if you say that it's not just 4-dimensional minimal surface, it's 4-dimensional minimal surface embedded in.
I think we would all be, I would be happier. I think we'd be happier maybe if somehow you wanted to say that it's something more radical, that this is sort of a 12-dimensional picture of the universe, and that there's an honest 12-dimensional object that we're talking about. Okay, there's some limit where things become effectively four-dimensional, but now I think I'm happier. So that there's a problem that the area double derivative acting on e to the minus area is ambiguous. If we just flat out
Yes, if you naively apply area
and
derivative.
the ambiguity is, and where is the ambiguity localized? Is it localized to the?
Oh, you take,
boundary of the-
you know, there is
Yeah,
this Hilbert transform.
Yeah.
You see, when you take ordinary minimal solution, it involves this integral of Hilbert transform, and you should find the second derivative. You differentiate it with respect to derivative, and you get this Hilbert transform at zero.
Coincident points, yes.
Yes, and it has 1 over delta. But then there is epsilon in the numerator because you have to approach from the above. So you get epsilon divided by delta squared, and that depends on the limit.
Okay, I think that then I'm much happier. So the four-dimensional, while the four-dimensional W of C is well defined, the four-dimensional double derivative is not.
That's right.
Period. And that's and so you have to find some way to lift it into a bigger space.
Exactly.
And some way to make it well
So,
defined.
that's right.
That is okay. That's at least a.
Yeah,
I'm
that's what I
tradition.
derived in my previous paper, which where I actually took honest number Goto thing and applied this integral, and I found indefinite results.
I think we would, I mean, just to say a kind of a general comment, I would be much happier if this was phrased somehow in the language of an anomaly, because it feels
It
like.
is anomaly. It
feels
is
like
anomaly
it would be
because
nicer to say that there's some anomalous term in the in the loop equation, because that's what it looks like, right? 'Cause
It is
again,
anomalous term which depends on the limits.
and also, if we say the word anomaly, then maybe we can check, Westernino descent. Anomalies satisfy lots of constraints, and so maybe we could, if we cast it in the
I
language
would
of
very much welcome you guys to find much cleaner way to formulate it.
Anyway.
The way I formulate it now, if you naively take minimal surface, you'll get anomaly. You'll get something depending on the limit. But if you redefine it as a limit from 12-dimensional space, then you get it right.
At that level, this is very much like the Westernino term, written as something local in 5 dimensions. That's all fun. That is all fun.
Okay, then guys, let me do more interesting things, because I have something much more interesting to tell you. So that's not interesting. Of course, I should add, they are equal, but in my imagination, I add s plus and s minus, because though they are equal, but their derivatives have opposite chirality, so whatever. And that's what I'm explaining about Nambo-Goto, this anomaly, epsilon divided by epsilon squared. Now, here is the most important thing. Two important things. One, how this kappa is related to G mu squared. And that's quite beautiful calculation. Let's take second area derivative. Let's take a small circle. Let's consider a small loop of the shape of the circle and find second area derivative in 2 points opposite to the circle, say, the same diameter at opposite sides of the circle. Say, if you consider a second area derivative, perturbative thing is very well known. You get f mu in one place, then you get this gauge factor from 1 to 2, exponential of integral a from 1 to 2, and then another f mu, and then opposite factor. That's what you get in Wilson loop if you take second area derivative at a very small loop. And then when you go to perturbation theory, you will get this formula. You'll get 1 over x1 minus x2 to the fourth, and then there will be this conformal tensor, which involves this. It is f mu, and because of conformal invariance, there's this delta mu minus 2x mu x mu. That's what conformal symmetry tells me. In this order, there is conformal symmetry. And of course, there is effective coupling constant. So that's what you get from operator product expansion. And let us find the projector which kills that term, because we want to see what is left non-perturbatively. So I claim the very simple projector, just antisymmetric combination of Kronecker deltas, actually does the job. If you multiply this projector times this conformal f mu tensor, after simple algebra, you'll get d minus 1 times d minus 4. So in 4 dimensions, it's 0. Okay, so we killed the leading term, the x minus 4 term, and then what is left must be 0-order term. And that is what is called gluon condensate. That has 0 order. It's just f mu becomes f mu squared, and then the rest is some unknown factor, which is perturbative W at shrink loop. The loop is very small, going to 0. So here is the constant. What do we get in my theory? You take the same thing, so we just compute second derivative of this perturbative thing. Now we do the same thing for this guy. And when we do that, it's rather simple what you get. You will get simple calculation. You take area derivative of my minimal surface. It's the same as ordinary, everybody's minimal surface. You just get this kappa squared. So you compare and you see that they are related. So this kappa squared must be equal to gluon condensate if you want this term to match. Actually, they have to cancel each other because they have opposite signs. Some of them want to be 0.
What happens when your second area derivative hits W perturbative in your sort of?
Well, that's what I computed.
Okay. Saying, so that was the first computation in terms of the gluon condensate is when it hits the.
Oh, the mixed term is 0.
Yeah, okay, that's sort of.
Yeah, it's
That's
symmetry.
when this is 0 because it's a single area derivative.
Yeah.
Sasha, just, what would happen if you said that, that you hit the naive, you take the naive loop equation acting on something goes like e to the minus perimeter. Does e to the minus perimeter solve the loop equations?
No.
No.
E to the minus perimeter is not even a loop, is not even a Stokes functional. It's not something which allows for finite area derivative. You see?
So,
You cannot
but
find
it's a-
area derivative of the
Right.
length.
Right. You can't define meaning that it's 0 or that it's singular. I'm trying to
It's
understand.
singular, it's singular.
Okay.
It's singular.
It's singular. So,
Yeah.
but is it
You
worse
see,
singular?
what is
than
area
what is
derivative?
area?
You change a
Yeah.
little variation, that
Yeah,
should be
but-
proportional
yes,
to area,
yeah,
and this
it's
one
not-
it
it's not.
doesn't.
No, but this one, it should be 0 then, right? You change it and the area doesn't change. Sorry, you're changing the length, so the area is not,
That's right.
so.
But
zero-
length does change. So
Yeah. Oh, I see.
so it is not proportional to area, therefore it is not what is called Stokes functional.
Yeah, I see.
So it's almost like square root of areas.
It contradicts the
right.
fact that it should be ordered exponential of gauge field, because for gauge field, this backtracking doesn't mean anything. And for your length, it does.
Yes.
That's what I call Stokes function.
Yes,
So it
yes,
doesn't
yes.
satisfy the basic properties which we presume. So that's why it is just the artifact of divergences. It is not a correct property of the function.
Maybe I'm just asking another stupid question. What if it's like an area, but it's an area in, such that, I don't know, what would correspond to, let's say, the like string tension getting bigger and bigger or smaller and smaller as a function of the size. I'm just trying to see like what, how surprising.
You could
is it?
imagine many things. I'm trying to say what happens with my solution, which doesn't allow for anything depending on anything. It's just constant.
Yeah, what I'm trying to understand is how non-trivial is it that the e to the minus area satisfies the loop equation up to these ambiguous terms? Is it already remarkable?
I think it is remarkable.
up
I
to
think it
even
is
forgetting
very
about
important
the-
observation,
yeah, right.
which reminds us that you should specify the vacuum when you are solving equations of motion.
All right.
Because usually
Yeah.
we know how to do it in ordinary gauge field, right? We find small fluctuations around that background field.
Right.
But here in loop equation, we don't know. I found the mechanism where that background field displays itself.
Do you have another example of a Stokes functional that's not area?
Yes.
What are some examples of Stokes functionals that are not?
It is integral x mu dx nu, which is a tensor, of course. But that's a tensor area. For the flat loop, it is area, but it is, for example, 0 if you make a.
I see. Yes.
So it is something which is
That would also satisfy the
No.
loop equation?
no.
That's
No, because its area derivative is just constant. Its area it will satisfy, but because it's not Lorentz invariant,
Yeah, yeah,
nobody,
right.
it's not interesting.
Yeah.
It's external field.
Yeah, I understand. Yeah. Okay.
Well, I can give you examples. This Dirichlet minimal area is the Stokes functional, and I
I mean the
can.
plateau problem.
Yeah.
Yeah. So that's another.
It's not trivial. It's not trivial. You could compute area derivative, and area derivative is fine. It's just d mu of area derivative which diverges. Area derivative for the Dirichlet is fine. It exists.
It's just not solving the equation.
That's right. So the way you make it self-do, okay, I'm not going to repeat. Anyway, last piece of information. Oh, let's get back to the momentum loop equation and see what this zero mode, which we found for the ordinary equation, corresponds to momentum loop equation. Well, if it is multiplication in physical space, it's convolution in momentum space. It's totally crazy thing. WFP, I say, it is integral over all loops Q times this G, which is this minimal surface transformed, of P minus Q times fluctuating thing of Q. So that is a symmetry which was totally invisible in momentum loop equation, but that's exact symmetry. We know that now. And the fact that this thing, as a function of Q, satisfies this equation is totally crazy, because this L operator applied to this G is algebraic, right? Remember, in momentum space, it's algebraic. Now, what it is actually, and how could it be zero? If you look at that, it turns out to be the following. If you have the real trajectory P mu, then it could not be zero as a local function of P mu. But if you have a complex trajectory, then complex antisymmetric form can be self-dual. You see, how can, what happens here is the following. You have area derivative in momentum space becomes something like that. P mu of theta minus times P mu of theta plus. To antisymmetrize with respect to mu and mu. So if you have two real vectors, antisymmetric products of two real vectors cannot be self-dual or anti-self-dual. That's a known fact in the theory of forms. However, for complex vectors, it can be true. So if you literally consider the Fourier transform and integral over real P mu, you will not find this solution. If you allow to change your contour and consider complex, then you will find those purely algebraic solutions. And that's something which is interesting to study. I didn't study it this way, but my self-dual surfaces present that solution because.
So what does WP look like then? In the end, is it still regular up to 8th order?
No, I think it is something like that. It is something which is delta function of P of this thing. It is zero unless this thing is zero.
Oh, so all of those perturbative things that you saw are just irrelevant.
We assumed that they are expandable and we came to contradiction, so we have to throw them into the window. And not saying that it's correction in the 8th order.
Oh, there's no, so it's not that it's the correction in the 8th order. Okay,
No, it's correction in the 0th order.
Fine,
in the
fine.
0th order, we
Okay,
assumed
good.
constant, and that in fact is singular.
Good. Okay.
So I think the solution for W of P, correct one, if you look at this, if you look at that transformation,
Yes.
that means somewhere in the complex space of these loops, there is a region where it's algebraically correct, but this is not a singular regular function, but some function concentrated on the support of this complex equation that P mu P nu is self-dual. Now that's a very interesting problem. I don't know how to solve it, but I know how to solve it in coordinate space. I presented that solution. But in momentum space, it looks funny because it is something algebraic which cannot be realized on real momentum. So there must be something algebraic, some curves, complex curves, which are self-dual. I haven't thought about that till the very end. I just have vague ideas, but answer is it's not analytic.
Mm-hmm. Okay. Not that it messes up in the 8th order. Yeah.
But let's end on a positive note. Here, helicoid. Let's actually try to do something with that solution which we found. So what is the minimal surface which would correspond to the spectrum we want to find? Let's ignore this perturbative part. Let's consider this minimal surface, which, as we now know, between us big boys is the same for 4 dimensions and 12 dimensions. So it's minimal surface. And the one which is relevant for the composite states of the string is known for ages. It's called helicoid. It's a surface made of rotating stick. And it's obviously minimal because it's just a rotating stick, so there is no external curvature anywhere. That's the definition of plateau problem. Anyway, it's helicoid. It's described by this equation for x. And you see, that's Minkowski thing. The last coordinate is tau, meaning that it is not rotating in place, but it is infinite. It's just a spiral going. It has infinite area, in fact, stretched into time direction, which is, of course, what we want. We want the bound state, which means it rotates indefinitely long around the circle. And if you view it as a trajectory in time, it is a spiral. So this spiral is a trajectory of a quark going around in circle and evolving with time. So that's this x is just actually equation of this helicoid in certain coordinates, and this is its metric. That, by the way, means that this thing is this line element. And if you consider simple quasi-classical calculation, you take this area. I'm already area per unit time. I mean, time is factored out. It's just Lagrangian because it doesn't depend on time. So it's integral dr, that's just a metric area element. And that is the length, it's, the quark with the mass sitting at the edge, and that's the world line of the quark. So that's mass term of the quark. Omega r is velocity. So that's a line of the quark, and that's this area of the helicoid. And when you add the condition that area that you want twisted boundary condition, you want derivative of that with respect to omega equal fixed angular momentum. So when you are fixing angular momentum, you do twisting boundary condition so that it's like Lagrange multiplier. You add the term such that the omega j, you add omega j term, and then you minimize everything with respect to omega, and that will give you the relation for classical angular momentum. When you do that and solve everything, that's a simple minimization problem, which is done, I'm sure, by many people. You get normal thing, which is called a Regge trajectory. That square of energy is 2 pi j, where j is angular momentum. I mean, it's not like my discovery, because I think that's how people are usually deriving the string, the classical string. However, people usually fight with vibrational modes, because I don't have them. In my case, I just have a rigid potential, a minimal surface. I don't have fluctuations of the surface. In my solution, there is no such thing as fluctuation of the surface. So my solution only gives this leading trajectory.
Well, I think by next time, when we talk, I think we do need to have a discussion about this subject, because you were, I mean, we can talk, there's lots of general reasons to expect the waves on the string, but this thing that you're dismissing about the lattice, I think we should dig into it and see, because this really was, just to say, because this is such a crucial point for the whole thing. Let me just...
Go ahead, make my day. That's what I was waiting for. Discussion.
But it's called,
discussion.
It's called the Lusher term, okay? I mean,
I will get it. Oh. I will get it.
Oh, you're gonna get the Lusher term. All right, great. So, but anyway, just to tell the kids. So, you know, imagine you have a very heavy quark here, another heavy quark here. Then the potential is supposed to go like alpha r. That's the, and this is the party line, right? So this is the string tension. So some m string squared r. But if you think that there's an actual vibrating string here, crucially with the waves that Sasha doesn't want. But if you have the waves,
it's not because of waves. It's because of something else.
Well, but anyway, I'm just saying in the standard picture, there's a Casimir energy that you can calculate. So
Casimir is not waves.
Right? Huh?
Casimir is not waves.
I know. The Casimir is not the waves, but it's but I'm just saying in the conventional picture, there's a Casimir energy that goes along with this and gives you a factor that's, I forget, 2 minus d over 24 times 1 over r.
And I get 1/6
Huh?
exactly.
Oh, you get 1/6.
Yes.
Okay.
Well,
Right.
it is actually 1/12. Yes, 1/12.
Okay, good.
I
Well,
get it.
Okay.
I get it from my solution.
Oh, then we can, then I'll be more, okay,
That's what makes me so happy.
okay.
Didn't assume it.
Okay, great. Well, then I would think you probably secretly have,
It is published.
but.
It is published already in archive. I get the following formula.
Yeah.
So that we know what we're going to
Yes.
talk about on the lecture 5. M squared equals pi sigma n plus 1 over 12. And that's this little term. That's what exactly follows from.
So you do get a correction.
Yes. This 1/12 comes from like something minus 1/6 in the
I wonder if we can,
Then how do you not have weights, like?
something like that. 1 over r times 1/6, something like that.
yeah, so how do you know that you don't have how do you know that you don't have the,
Vibrations,
Yeah,
I don't
the
have these
vibration.
degrees of freedom.
Well, I mean, it's not.
No,
it's
you
not-
see,
how-
when I will
how do you
find,
know?
so
Yeah.
far you don't know,
Right,
because
right,
there is this,
right.
what I call fluctuating thing. I will present this fluctuating thing, and this also rigid. It's also expressed in terms of the boundary plus one thing, which is area integral. I will get,
Maybe I can ask the,
no, I do get area integral. There is some anomaly which gives me area integral also, and that area integral gives me this correction.
mhm.
But this area integral doesn't have
Maybe-
infinitely many
just-
degrees of freedom.
We're jumping ahead again, but do you have daughter trajectories or just leading Reggie trajectories?
I have trajectories classified by certain internal quantum number, but it's not the same as vibrations.
But qualitatively, is it?
Qualitatively, it's equivalent to dotted trajectories, yes. There are some
you have
internal quantum
exponentially-
numbers regardless of J.
Do you see exponentially many states? Do you have a Hagedorn spectrum, roughly?
Yes, I do have, well, my states are classified as follows. Here is a unit disk, and there are twistors in complex plane, and there could be as many poles inside the unit disk, and that number is my topological quantum number. So I do have integers of which classified trajectories, but there are other internal numbers, moduli, I don't know that. At least I know that there are classes, because the number of these singularities inside the unit disk is topologically invariant, because when this singularity approaches the side of the disk, there is a barrier.
Mhm.
So that's all I know so far. But that's more than I should be telling, because I didn't explain.
Yeah, sure. I just wanted to, yeah, I mean, okay.
No, but there is
Okay.
something which is rich enough to describe what we see.
Okay.
At least. I'm not saying that I have solved everything. I'm just saying that I have a candidate which is very, very promising.
Just check one thing very. Sorry, are you sure about the sign? Is it positive or negative?
Positive.
This is negative.
Well,
The Lucia correction is negative. I think,
Where?
I think the,
no, maybe it is.
the-
I'm not sure. No, I'm sure about this side.
that sign is for sure.
Yes.
Hmm.
This side, otherwise it will be negative. It will be cos. No, it is positive here.
It is positive there.
And I think here it is
But,
also positive. Yes.
Okay,
No, look, they are in one-to-one correspondence, so if there will be different sign, there will be different sign here. It's
no,
different
but
sign.
that's why I wanted, I mean, these are, they may or may not be, these may or may not be related, but this should be kind of like,
What you wrote, by the way, is negative, right?
this is negative, this is supposed to be negative, yes. I mean,
So
that's,
why
that's
did
the,
you
cas-
correct
the,
me?
the bosonic Casimir energy is negative.
So,
That's right.
so then it's right?
Huh?
That's what I wrote.
Yes, there it should be, yes, there should be sigma bar minus 1 over.
But this
yes.
minus goes
That's
into
right.
this plus, yes.
Okay, okay.
Because the first formula is just a redshift trajectory, or no? The first formula you wrote?
That is something which you would expect, yes.
Yeah.
And
It's
that's
just-
something which is like Casimir effect. In my case, it comes from the term which is comes from the area integral. Look, I don't want to spoil the.
No, it's fine. Yeah. I just wanted to just checking what the precise here. Where's Coody?
So for the spectrum, is it
No,
plus 112?
no, yeah, for the, just gonna get,
For the
I
spectrum.
don't think anyone knows for the spectrum. Because, yeah, no one knows for the spectrum. I don't think anyone knows for the spectrum. This is something you can measure on the lattice.
Yeah,
So that.
but I have both.
Okay, great. So let me just remember the precise coefficient. Yeah, this is the guy that I know, who I trust. And sorry, just 1 second. There it is. Okay, so this is the formula. Sorry. This is the formula. There's even a pi. Sorry, I forgot. There's a pi.
No, well,
Yeah.
pi is
Yeah.
everywhere, of course. Sigma times pi, yeah.
But this, yeah, but it is.
Oh, there is pi here.
Yeah, so it's minus pi, yeah, it's minus pi over 12R. That is the claim. The potential goes like minus pi over 12R.
Yeah. Well, we'll see. Let me show you my formula. If you want to see my formula, I can show you.
Yeah, and this actually, when this talk was given in the mid-2000s, this was not well measured on the lattice. But, I was looking from like 2 or 3 years ago, people claim that it's measured to within like a few percent on the lattice. We could argue whether they're right or not. I mean, that's a separate argument, but that's, yeah. And again, this is normally considered to be yeah. For obvious reasons, it's a universal prediction.
Let me show you, once you asked, let me show you my formula. Mm. Um,
The other page, there are 2 columns.
Oh, so it is something like that. I'm minimizing, so it's only in the end we get this. In terms of R, it's different R really, so I'm not sure it's correct comparison.
Yeah, well, we'll take a look for next week.
Yeah.
It looks
Well,
like,
anyway, in the end, I know very well that it's n plus 1 over 12. And it couldn't be different sign because otherwise it will
Yes,
be
you
negative.
have-
So
well, but right. Mhm.
so there is something, that's the energy quantization. Look, it's not one-to-one comparison, but I have that's this term, pi over 6, a term in the energy. minus pi over 6.
But you also have a pi in the first term. I mean,
So I have it with a plus sign, but there are other terms when you compute. So it's
yeah,
not
but
the.
if you look at equation 17.12, right? The
Yes.
next equation down. So it looks like you have the ER is those two terms. Oh, that looks it's funny. I mean, the part that goes like 1 over R should have a pi in it.
Well, it is.
No, the part that goes like 1 over R. No, but you have 4 pi ER. When I divide by E itself, should have the pi.
You mean you won't have pi in denominator?
The way you have it, it just cancels, right? Your E.
No. If I take this pi out, then it will be sigma r squared plus 1 over 12 pi. I mean, I think.
No, but I think that the sigma, you could absorb the pi into what you mean by sigma.
No, but I don't think it is absorbed in the potential. In potential, it is actually sigma. Pi comes from angles.
Uh-huh. So, but no, in this, I mean, in this potential, it's really sigma, directly sigma. It's just length, right?
Well, if you normalize directly sigma, you
Yes.
should take pi out of here, and you'll get sigma r squared plus 1 over 12 pi.
Right, but I think, well, but then there'll be pi downstairs, not upstairs. But the Casimir energy is a pi upstairs. Yeah.
Well, here is pi upstairs. Look,
You can't have it both ways.
Yeah.
It's one or the other, but
guys,
Yeah.
I don't want to be responsible for intermediate formula.
That by next time, I want to like delve into this issue. Also understand how much we can trust the lattice for this, because definitely in the mid 2000s, I mean, 10 years ago, even 15 years ago, you could not trust it. But I've seen some recent papers where people are very confident that measured this thing.
Look, let me,
Yeah.
I can tell you that this term comes not from vibration or anything. It comes from what I call the Liouville term. I have in my energy.
Then it makes a lot of sense, because the Liouville term, of course, scales the same as Casimir, right? I mean, it's normally there to compensate.
I
for
have a
Casimir
Liouville
on
term,
the
gradient rho squared,
Yeah,
and that rho is related to Caesar. So,
but then it really makes perfect sense, because for you, it's a classical thing. Here, it's a quantum thing, right? But that's as the usual Liouville story. So you can have when there's a quantum anomaly, you can have some.
my Liouville term comes as quantum anomaly, but it is rigidly related to my area. Guys, I'm going to gladly talk about all of that.
Great, yeah, no, I just wanted to flag it, so we can
Yeah.
make sure to talk about it next time. But maybe, Sasha, we can try before next time, just to get all the pies and everything straight, and just see if there's a clean.
Oh, I will.
Right, yeah.
No,
And then-
it will be actually lecture number 5. Excuse me for that, because next one will be first step, which is how do I get perturbative QCD out?
Yes, that's right. Yes.
That's very interesting. How do I get planar graphs? Because
Yes.
I have something which gives planar graphs, and after magic transformation gives also this Liouville term.
Right. Okay. But
So I think,
but if you say it's coming from something, if you're saying it's something coming from a Liouville mode, at least it makes sense that it looks the same. I mean, that
Okay.
now it really is about the detailed coefficient. So that's okay.
Look, I'm not playing with coefficients. I didn't fit them.
No, I know. That's what I'm saying.
So if my coefficients are wrong,
That's-
sorry,
yeah.
I don't have any others.
Yeah, exactly. Yes, yeah, that's yeah. Also here, I mean, this in this conventional string picture, you cannot mess with this, period. You make a string long enough, the only excitations are the transverse ones. This is a universal prediction. That's why people were excited to test it on the lattice, just
Yeah.
yeah.
Well, I say they don't test string, they test something which is so general, it comes from rigid string as well as physical string.
If you agree with this number.
Yes.
So that's why a lot is going to depend on whether you agree with this number. Yeah.
Yes.
Right. Excellent. I mean, if
Okay.
that's true, that would be really, really fascinating, because this, anyway, yeah, great. Sorry,
Okay.
sorry for.
So, I mean, let me finish my lecture. Where is it? Let me finish my lecture. So my lecture basically is finished. What I'm trying to say, a little bit of philosophy, that there is this, what I say, illusion. Classical soft film transition between topologies, and classical film has and why transitions, because it has physical degrees of freedom, and they probe the space of all solutions, and some large fluctuations of this shape could bring them to disk or catenoid or whatever. If I say that the string is an illusion, is a holography, a ghost, then there is no such thing. It's just representation of the true instanton or whatever vacuum, and it is not some physical object having physical string tension or anything. That's what I claim. The solution I have doesn't have any room for physical degrees of freedom of the string. It has something else, which I'm going to describe, and these are indeed degrees of freedom on a surface. But these degrees of freedom are almost rigid. They are all reduced to quantum anomaly. So the core principle is that, where is it? I don't, because it is not a correct view. I want to show you core principle. Core principle says, why it is not visible? It was visible on my.
You'll just have to tell us the core principle.
Core principle is you should minimize the energy of the quantum system, not impose on the quantum system the properties of the model built for to mimic confinement. You have to start from QCD, not from rubber band. And don't impose on QCD whatever you know about rubber bands. So, zero mode, so summary. The multi-instanton vacuum is geometrically represented by a rigid surface with anti-self-dual area derivative. Goldschmidt additivity to satisfy nonlinear factorization of equations. This area function must be strictly additive, no topological phase transitions. And then there is this Hodge-dual geometry. If you embed it in 12-dimensional space, then you have indeed self-dual area derivatives. There are hidden variables which make this paradox that the value of the area doesn't depend on chirality, but area derivative in this embedding does depend on chirality. And then operator for the expansion, once you project out this conformal operator for the term related to the perturbative QCD, then you match the terms and you get relation between vacuum F mu squared and my parameter kappa. And next lecture will be how to place Majorana fermions on this rigid surface to imitate planar diagrams, and that is done by means of Pauli principle, canceling the non-planar cancellation. That's the next thing. So I basically entered the shrine of string and said that it is not theory of everything. But I really have deepest respect to the string theory, because all the tools, all the technology I'm using is borrowed from string theory. I just don't share the philosophy. But I definitely benefit from the tools.
I think not many people have the old philosophy anymore anyway, so it's but anyway, yes. I think most people have it's a good tool philosophy. Perhaps too much actually, but anyway, I think even most yes. I think if you go talk to a random string theory grad student here, you'd be surprised how little they know about string theory.
Maybe.
Almost nothing.
Well, look, there is also a dissent in the physics community, because physics community feels that they were, went for 40 years in the
Yes.
desert.
Yes, that's true.
That is long enough, and they don't see promised land.
It's true. It's true. It's true.
You can stop the recording now.
Yeah.
No, but look, joking aside,
Yeah.
I mean,
Yeah, I think.
string theory is totally the master key to this all technology. So it is really very stupid to say that it is wrong. It's not wrong. It's just not universal, but it can be used for various things, and I'm using it also.
So Sash, let me ask you a question. I mean, this is, I'm just
to dive.
I'm trying to go to the
But-
usual. So, look, I know you don't want to talk about like, you weren't talking about heavy quarks. But let's
Hold
say
on, let me now, once we're on questions, let me let me do it better. Then you will pass it to the next.
Sure. Let's say I have two heavy quarks, a quark and an anti-quark, right? Very, very heavy.
Heavier than the cutoff.
Yes.
That's what you mean.
Yes, I mean, they're there in the real world. They're called tops. So let's say we have tops.
No, they are not heavier than ultraviolet cutoff,
Well, no, they're not.
which is Planck mass.
Yeah, no, I don't want them to be, no, but I just want them to be heavier than the QCD scale. I don't care that
Yes.
they don't have to be at the cutoff. But you know, I stretch them far apart. I'm just going through the conventional story. There's a string that forms between them. And what that means is that first, the potential goes like R, but second, it means, you know, that if you take this quark at this end and wiggle it, then the quark at the other end does not immediately wiggle as well. It doesn't feel a force or anything. You know, it takes some time. The wave goes down and it hits the other end and something. Now, what would happen in your what happens in your model?
Well,
What
first of
happens if
all,
you have
I'm
equal-
considering n equal infinity.
Yes,
I have infinite number of colors, so
Yes.
that's idealized world.
it's true. It's true. It's an idealized world, but I can still talk about heavy quark sources in this world. And I mean, I get this linear potential between them. And now on one end, I take the quark on one end and I just move it suddenly. What do you think happens to the other quark?
Look, when I'm considering actual path integral over quark trajectories, regardless whether they're heavy or not, there are fluctuations of other degrees of freedom around the quark trajectories.
No, but I'm talking, but I know you want to talk about that, and I want to talk about something.
No,
I
I'm
wanna
not,
talk
no,
about-
no,
yeah,
different thing.
yeah.
So what I'm trying to say is my solution is that for the fixed shape of the trajectory,
Yes,
if you want to insist on a fixed shape of physical trajectory or a phase-space trajectory, I don't know which one.
I mean, my question is not about the formalism. My question is a physical question. I have two heavy quarks. I've stretched them far apart from each other. They're just sitting there. And then on one end, I take it and I move this. What happens?
Well, in my
Yes.
approximation,
Yes.
infinite n solution of loop equations,
Yes.
there is instant interaction like potential kind. It is minimal surface,
So
indeed.
But this massively violates relativity. The other
No.
end can't.
It's totally compatible with relativity.
We cannot have arbitrarily rigid objects in relativity.
It's not
I have to
rigid.
think
It's
that-
not an object.
Well, no, but this is what I'm asking. Does anything happen to the quark at the other end? I take this one and I move it. Does anything happen to the quark at the other end? In the standard picture, it takes a time, the speed of light for the information to reach, and then it feels a big force that yanks it up. Right? What happens in your picture?
Oh, it definitely doesn't contradict relativity. And if I really,
Maybe you say nothing happens there. It just sits there. You just move this and nothing happens.
no, because my effective action,
But okay, if nothing happens, then either it happens instantaneously or it takes some time. So what's happening in this intermediate time? I mean, this is the way we normally argue. There's waves, right? This is the high school argument why when you have relativity and you have any kind of long range force, even one over r squared, never mind r, you know, which is If you have any kind of long-range force, relativity implies waves. Because of this argument, you do something here, you wiggle something here, and in order to be compatible with relativity,
I
it
do
has-
have waves, okay. Because in addition to minimal area,
Yes.
I also have my Liouville integral. And my Liouville integral, I think, describes your waves. Because what is my Liouville integral, which is effective energy, is non-local thing, which is integral over the surface.
Okay, but we have not seen this yet.
No.
Okay, all right.
And that is dz rho squared divided by whatever. And this rho is depending on the boundary values. There are boundary values of this loop and stuff. And this rho is holomorphic continuation of resistors from the boundary inside. So when you shift something on the boundary, this rho fills inside. So this whole integral changes. But it's not like at every point there will be waves. It is that this change propagates all over the place because this rho depends on the boundary values.
I think I can actually tell that this is a little, maybe we can talk about this more next time, but
You have very interesting question. And that term actually leads to Lucier term. So indeed, there is non-local interaction.
okay.
Yeah.
I want to now, I'm just going through the standard arguments why there's waves. So let me make it, let me do it so I don't have to talk about the heavy quarks, okay? So this is just a standard trick. I'm sure you know this trick very well. Imagine that I have QCD, right? But I do the following thing. I mean, there's many ways of doing this. By hand, I vary the gauge coupling. Okay, so I vary the gauge coupling, or even better, essentially what I want to do is that here lambda QCD is where it is 1 GeV. And I vary so that lambda QCD here is Hubble, you know, bigger than the universe. Okay, so that means that effectively it's not confined out here, right? But there's this big region of space in the middle where it is confined, right? Now, let's say in here I start with a heavy quark. Now I'm going to get rid of these heavy quarks, but just to start with, I start with a heavy quark and an anti-quark, right? But now I'm going to pull them apart. Okay, I'm going to pull them apart. So here it's confined.
And you
so
don't
this
let
thing,
pairs
right?
born in a vacuum.
No, there's no pairs because everything is heavy. Everything is heavy.
No, just because
Right.
it's heavy,
Yeah.
because of infinite number of colors.
Yes, exactly. Also that, of course, yes. But now I'm going to pull them out. And then you see now that after it gets out into this region, now they're not confined anymore, right? Now they're not confined anymore. So here I see the colors and everything. Now I can move this out to infinity, okay? And what I'm left with is this nice, I mean, in the standard picture, there's this nice QCD string, which is sitting here. Of course, the string has some color charges that come out this way, okay? But this is now a nice QCD string, which is sitting here in this system. I just told you a way to produce it. I told you a way to produce it by taking a quark, anti-quark, pulling them apart, and then throwing them out. But that means that in this system, there's a solution that looks like this string, okay? So far, we're not saying anything about vibrations, but we're just saying there is a solution that looks like this kind of tube of energy.
I have it also. I don't have vibrations, but I have it.
Exactly. However, now we have Goldstone's theorem. See, this is a solution that spontaneously breaks the translational symmetry, just like a rope. This is the reason why there's waves on a rope, right? Because if we take the atoms, if we take whatever the balls and springs that make up a rope, there is a solution where the rope is here. There's another solution where the rope is here. There's another solution where the rope is here. The rope itself is spontaneously breaking translations in this direction. The moment we're spontaneously breaking it, there must be Goldstone modes by the standard argument that if instead of just rigidly translating everything up, I look at a very long wavelength translation, then this thing has almost the same energy as the initial state, and therefore I've produced a wave. I produce a configuration whose energy goes to 0 as the wavelength goes to as the wavelength goes to infinity. That's the usual argument why there's waves on a rope and Goldstone modes. So that's the usual argument why if you have a string, there must be waves on it, right? And the reason I went through this whole business about the quarks and antiquarks is that if I was forced to have the quarks and antiquarks here, well, the quarks and antiquarks themselves are breaking translational symmetry. So you might be free to say that there's a rigid dumbbell object between these guys. But after I do this thing where I pull them apart and take them away, I'm just left with this object that's sitting there as a nice solution of the theory. So there needs to be some waves on it. That's the argument. So we should, I mean, the Liouville mode could be nothing. There could easily be additional modes on the string, no problem. We can have Liouville modes. We have all kinds of other modes on the string. But there must be these massless modes on the string that correspond to the waves from this argument. So I think we should try to go through.
Yes, I would love to discuss it, but I think there is this miracle of taking n to infinity and suppressing all kinds of fluctuations. Not all, but maybe some kinds of fluctuations.
Yeah, I think that will not. I think that doesn't do. Anyway, let's discuss it. But I think since this is such a central point.
Yes, I agree.
Try to get to the bottom of this.
But I have to get there first.